C of x is equal to L of x. In this case, you'll see that the forced lane change cost needs to be less than or equal to 1 over alpha, which we've already talked about is the expected distance traveled between first attempting to lane change and actually completing the lane change. The other thing that's interesting about this is that we can vary this. This only has to hold locally for each cell individually. So what that means is that we could, for example, for some roads, vary alpha because lane changes might be more difficult because those roads are faster traffic or more traffic than for other roads, or maybe it's easier to lane change at midnight than it is during rush hour. As long as this condition holds locally for each cell individually, a cost function is monotone, and our Dijkstra's-like algorithm will work. This is where the dirty laundry comes in. Because of monotonicity, there is also a limitation on the expressiveness of the policies that we are able to obtain. Specifically, you'll never get a policy that allows for cycles. So in this case, where if we wanted to lane change from the right into the left lane and we missed it and went around, the policy won't allow us to do that. The policy will have a forced lane change before the loop. In practice, this doesn't tend to matter all that much, but this is the price we pay for the computational efficiency of Dijkstra's. So let's apply our algorithm now to the example from the beginning. So what I've done here is I've colored all the cells in this lane graph according to the optimal policy. And specifically, a green cell means stay in lane is optimal. A yellow cell means change lanes is optimal, and the hatch pattern tells you in which direction the policy wants us to lane change. And the red cell means a forced lane change is optimal. And again, the hatch pattern tells you in which direction. So in this case, you can see that starting from point S, the policy has us continue along the rightmost lane for a while, but then quite far away from the intersection where we need to left turn, it tells us we need to start thinking about lane changes. We can also get some really nice emergent behavior out of this router with very simple cost adaptations. If you're driving on a high-speed road and there is a merge lane coming up, a good driver will often go into the left lane to prevent having to brake hard for someone that might merge in front of you. So what we've done here is we've added a cost on traversing any cell that has more than one predecessor, so basically the cell that comes right after the merge. And what you can see is that the policy is having us lane change out of the rightmost lane just before the merge. And then after the merge, it has us lane change back into the right lane to reach our target at G. And then for my final slide, I want to leave you with this video of the router routing across the entirety of Houston. I've had to slow this down by 50 times right roundabout to make it visible what's happening here. As you can nicely see the fronts of the algorithm expanding. This took somewhere between 150 and 200 milliseconds on a work desktop. So this is very much applicable to real-time autonomous vehicle routing. And with that, I want to thank you for your attention, and I'm looking forward to your questions. Thank you.
Thanks, that was great, Max. Have our next speaker come to set up.
Trying to steal your microphone.
No, we're good. So go ahead and get your, do you want to just hold it or you want to click it? Whatever is easiest for you.
I'll just hold it.
Great. So our next speaker is Saurav Agrawal. He's from UNC Charlotte, and he's going to talk about his paper on the correlated arc orienteering problem. Thank you. Go ahead and take it away.
Hello, everyone. Our paper is titled The Correlated Arc Orienteering Problem, and it is co-authored with Srinivas Akela. So let's first look at the orienteering problem. In an orienteering problem, we are given a graph G with a vertex set V and an edge set E. We have rewards on the vertices V, and we have cost on the edges E. And we are given a robot with a finite budget. The task is to find a tour or a path such that the sum of the cost for the tour is within the budget, And we need to visit a subset of the vertices such that the total reward collected is maximized. The team orienteering problem is the generalization of the orienteering problem with k-robots. Next, we'll look at the arc orienteering problem, wherein again we are given a graph G. However, over here, the rewards are on the edges instead of on the vertices. We have cost on the edges, and we are given a robot with a finite budget. And here, the task is again to find a tool such that the sum of the cost is within the budget. However, we are visiting a subset of the edges instead of a subset of the vertices in the orienteering problem. And we want to maximize the total reward that is collected from the edges. The team orienteering arc routing problem is generalization to k-robots. You et al. Gave a generalization of the team orienteering problem, which is known as the correlated orienteering problem. Over here, the rewards are correlated. What this means is that visiting a vertex can provide information associated with a correlated vertex. And it is defined by weights, which gives a fraction of the reward associated with a vertex V that can be collected by visiting another vertex V prime. They gave a mixed integer quadratic program formulation for the problem. In this paper, we introduce a new problem called the correlated arc orienteering problem, where the rewards are associated with the edges, and they are also correlated with each other. So this means that visiting an edge can provide information associated with the correlated edge. And these correlations are defined by a weight function, which takes in a pair of edges and gives a fraction of the reward associated with an edge E, collected by servicing another edge E prime. So this problem is a generalization of the team orienteering arc routing problem, as TOARP does not consider correlations, and we are considering correlations between the rewards. It is also a generalization of the correlated orienteering problem. So we can model rewards on the vertices by treating those vertices as degenerate edges. And so we can model both vertices and edges in the same framework. So hence it is a generalization of the correlated orienteering problem as well. So let's look at a simple example. Over here, we have a spiral pattern composed of 77 line segments, each of unit length. We assign a reward of 1 for each segment. And we have correlations based on the field of view. So over here, the blue box shows a field of view such that traversing an edge can observe immediately parallel edges. So here are the solutions using an AOP formulation on the left and CAOP formulation on the right. The AOP tool covers 53 segments, whereas the COP optimal tool covers 69 segments. So we can see that COP is able to exploit correlations to generate more exploratory solutions. So using this idea, we were able to also apply it to coverage of road networks, where we are given an input urban road network, and then we are given a team of robots. And the COP formulation can utilize the field of view to generate efficient routes that cover as much as the road network as possible. So let's formally describe the correlated arc orienteering problem, which we do by formulating it as an MIQP. So we are given a graph. We model the environment as a graph, which is undirected and connected. We also have depot locations in the graph from where the robots start and end their tours. We are given K robots with individual capacities Q for a robot K. A unique characteristic of our formulation is that we have two modes of travel, servicing and deadheading. When a robot take actions such as taking images, then we say it's servicing and there is a cost associated with it. And when a robot is transiting from one vertex to another, then we say it is deadheading and there is a cost function associated with it. We have servicing variables that are binary, and we enforce that each edge can be serviced at most once. We have deadheading variables that are non-negative integers. So this means that any edge can be deadheaded as many times as required. And the task is to compute a set of routes. So now we can formulate the capacity constraints for the robot. So the total cost of a route is given by the summation of the service cost plus the deadheading cost for the edges that are being traversed in the route. and this cost should be less than the given capacity of the robot. So now let's look at the rewards and the correlations. The reward function is a non-negative real for the edges. And we have special correlations that are modeled using the weight functions. For a pair of edges, it gives a non-negative real value. And these represent fraction of the reward RE for an edge E that would be collected by traversing another edge E prime. We define a set of neighbors NE, which corresponds to the set of edges that can observe another edge E. So when we service an edge, then we collect a reward equal to R of E. However, when we do not service an edge, then we can collect a reward through correlations by visiting the neighbors. And this gives us the expression for the total reward, which is a combination of the above two cases. And this is quadratic because we have two variables being multiplied. So now we can give the MIQP formulation where the objective is maximization of the total reward. We also have total cost term, which helps in optimizing when the budget is very large. We have constraints that for servicing, which says that we need to visit each edge at most once. We have sum of weights as the constraints. We have capacity constraints, and then we also have routing constraints, which ensures that each individual route is connected to the respective depot. And then we have variable bounds. So now the COP problem is NP hard, and solving the MIQP to optimality can take a very long time. And thus we develop new heuristic algorithm for computing routes rapidly. There are three important steps that are performed iteratively in the algorithm. First step is to maintain a set of visible routes. Then we greedily select an edge that needs to be added to a route, and then efficiently construct a new route by adding the selected edge. We have an additional compute route heuristic, which is a constructive edge insertion heuristic that runs in linear time. And this helps in bounding the overall complexity of the algorithm, which is O of M cubed, where M is the number of edges that have positive rewards. So we have the reward function and the spatial correlation, which was given by the weight function. We defined the set of neighbors, which were corresponding to the edges that can observe an edge E. We now also need to define co-neighbors that are the edges that an edge E can observe. And this gives us the definition of utility of an edge, which is the reward associated with the edge plus the total sum of the rewards it could receive through correlations. And then we have the greedy selection criteria, which is the difference in the scale utility and incremental cost of adding an edge. With this as the greedy selection criteria, we select edges. And then once we have incorporated it into a route, we update the scaling factor and the utilities. So we applied COP to an environment monitoring problem where we wanted to estimate the methane gas leak rate from oil wells. And these oil wells are shown as blue dots in these figures. And we're using a ground robot to find routes on a road network. We model the rewards as expected entropy reduction. And the correlation weight function is developed using expected square distance between the edges. So we compare the greedy algorithm with the MIQP solution for a data set of 100 road networks from the Permian Basin in Texas. And we could obtain solutions within 8 milliseconds for each of the environments. And on average, the greedy solutions were within 9% of the optimal MIQP solutions. So to summarize, in this paper, we introduced a new problem, the correlated arc orienteering problem, that considers correlated rewards on vertices and also on edges. The formulation is a generalization of the team orienteering arc routing problem and the correlated orienteering problem. We developed MIQP formulation to obtain optimal solutions. We developed a greedy algorithm that runs in O of M cube time.